In this video, we're going to talk about this theorem here. Whenever you're given y equals x to the power of n, if you differentiate this here, which is dy by dx, it will give you this thing here. So whenever you're given y equals x to the power of n, when you differentiate it, the n goes down here, and so that you have n here, and then the n here itself will minus 1. So you will need to minus 1 here. So whenever given y equals x to the power of n, if you differentiate it, it will give you this. Okay, that's basically what this theorem here is saying. This here is just another notation. It's just the way we write it. So when you differentiate this thing here, remember this is like y itself. So it's like me writing d and then dx of y here, which is the same as dy by dx. Well, in this video, we're going to talk about this theorem here. Okay, so in some of the early exercises, I gave you, I asked you to differentiate y equals x squared, and the way we did it was we first sketched the graph and then set up our points A and B, and then the true gradient that exists between A and B is when you start to take the limit as h tends to 0, and then you would then multiply this thing out. That would then give you this here, and then well this. You take it down here like this. If you don't understand this, then watch some of the earlier videos, okay? And then blah 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 blah, and the answer dy by dx, which is the true gradient, is given by 2x. So when you're asked to differentiate x squared here, it will give you 2x, and this here tallies up with our theorem above. You see, whenever you try to differentiate x to the power of n, the n here goes down here, which is true here, because this here goes down here. That's why you've got this 2x here, and then the power 2 itself gets minus 1. That's why you have 2 and then x to the power of 1. Well, x to the power of 1, we don't bother putting the 1 in here, so it becomes 2x. So my point is that when we try to differentiate x squared, it gives us 2x, which tallies up with this theorem here. This theorem here was our original theorem here. This is our original theorem. Okay, and the point is that when you differentiate x squared, it gives you 2x, which tallies up with this. Okay, so the next example, well, I also gave you this as an exercise. Differentiate x to the power of 3. Again, sketch your graph, set up a and b, and then start to take the limit as h tends to 0. And then you would then have to power this, power 3. Well, you would have to multiply by itself 3 times. So merge these two together. That will give you this. And then now you've got to do this times this times this times this, and then this times this, and then this times this, and then this. It's quite tedious, but in the end, you will get to 3x squared. So when given, when asked to differentiate x to the power of 3, this 3 here goes down here. That's why you've got this 3 here, and then the power itself gets minus 1. That's why you've got 2 here. 3 minus 1 is 2. So when you differentiate this, it will give you this. And again, this tallies up with our theorem here. Okay. So this goes down here, and then the n itself gets minus 1. That's why you've got this. Here you can see that here. Okay. And well, you can extend this. Hang on. Hang on. Let me move it across. Hang on. Well, so you can also extend this to y to the power of 4 here. You would use the same process. First, sketch your graph here. Remember, x squared is a bit flatter. X squared will look something like this. So x to the power of 4. Well, x to the power of 4, roughly sketch your graph, set up a and b, and then start to take the limit as h tends to 0. And then you would follow the same process, but this time you multiply by itself 4 times. Very tedious, but it can be done. So merge these two together. That will give you this. merge these two together, that will give you this. And now the long process of doing this. This times this, this times this, this times this, and then this times this times this, this times this, and then this times this times this, and this times this, and then you've got to take away x squared there. Hang on. Yeah, you got to take away x squared there. Oops. Well, anyway, and then in the end, it will, hang on. So x to the power 4 here. Follow through the whole process, and then it will take you to it will give you the answer dy by dx as 4x to the power 3. So hang on, when given this here, hang on, let me move this. Bear with me. Let me move this. Okay. When you try to differentiate x to the power 4 here, the 4 here goes down here. That's why you've got a 4 here, and then the 4 here itself gets minus by 1. That's why you've got a 3 here. Again, it tallies up with our theorem here. Okay. So yeah, even I actually gave you this. Even if it's a square root, you can sketch your graph, set up a and b, and then start to take the limit as h tends to 0, and then you would blah 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 here. Remember when you get to when you get to this stage here. Hang on, let me think. When you're here, remember that you times top and bottom by the conjugate of this, and remember the conjugate. We did lots and lots of exercises on this in the section on limits. So, after a while, you get to have a gut instinct that whenever you see something like this, to work out the limits, you times top and bottom by the conjugate of this, and it's just something that we've done so many times that we just know inside our guts that we have to times top and bottom by the conjugate of this. So that would then take you to this, and then blah 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 here, blah 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 blah, and then this here is your final answer. Okay, so dy by dx here is actually this, but this is actually whether you can always visualize square root of x as x to the power of a half, and then when you differentiate this here, the half goes down here, so it becomes a half x, and then the half itself gets minus by 1. So a half minus 1 is minus a half. So when you differentiate it, it will give you this. But when we differentiated it, it gave us this. But the point is that this is exactly the same as this, because when you can visualize this as well, you can break up this fraction. Break it up along here, so it's like a half times this thing here. So when you times top, bottom times bottom, it will give you this. So my point is that this is exactly the same as this. Okay, and then the square root, you can turn that into x to the power of a half, and then this whole thing here, you can visualize it as well. Whenever you have x to the power of minus a half, you can immediately jump to 1 over x to the power of a half. So here you've got 1 over x to the power of half. You can jump backwards here to give you x. Well, it will then give you this. Okay. So my point is that when given y equals x to the power, so when given y equals the square root of x, you can write the square root of x as x to the power of a half. Okay. So when you come to differentiate it, so at the moment we've got y equals x to the power of a half. So when you differentiate this goes down here, and then the half itself gets minus by 1. So that's why you get this. And again, it tallies up with this. Okay. Yeah. Even if you have a weird fraction here, it will still work. This theorem here still works, even if you have this. This will then go down here. That's why you have this here, and then the 3 over 7 gets you have to minus this by 1. So 3 over 7 minus 1. Well, minus 1, I'm going to visualize it as this. So that equals minus 4 over 7. So that's why this thing here is minus 4 over 7. And even if it's like this, even if you have a decimal like this, you take this down, so it's like this, and then this power here itself gets minus by 1. That's why. Well, when you try to differentiate this, it will give you this here. Okay. At a later stage, we will prove this. We will prove this theorem here. But for the time being, we're just going to accept it for the time being. In the future, we will prove this theorem here. But in order for us to prove it, we need to have the knowledge of the binomial theorem. And basically, the binomial theorem is that when you have something like this here, x. Well, at the moment, I haven't shown you the binomial. Oops, hang on. I haven't shown you the binomial theorem yet. We will do this in the future. But basically, the binomial theorem allows you to multiply something like this. So normally, if you're asked to power x plus h to the power 5 here, then you have to do this, and which would take ages because you've got to get this times this, this times this, this times this, this times this, and then later on this time. It would take you a long time to work this out here, multiply everything together. The binomial theorem allows you to, hang on, let me move this across. The binomial theorem allows you to multiply this out easily. The binomial theorem here allows you to multiply this whole thing out easily. Basically, when you multiply this whole thing out here, you would get something like this. Okay, the binomial theorem allows you to work out the coefficient in front of this. So basically, when you multiply this whole thing out here, you would get something like this. It's just that the coefficient here changes. So this here, I don't know, it could be 17. This one could be, 13. This one could be 7. I'm making all these up here. Something like this. The binomial theorem allows you to work out but basically, when you multiply this out here, it will give you something like this. The binomial theorem allows you to work out the coefficients here, and then basically you can work this out easily. Otherwise you have to do this times this, this times this, this times this, this times this, and it takes a long time. The binomial theorem allows you to jump straight to this, and it's a lot easier. Okay, and then when you come to do something like this here, the binomial theorem allows you to work this out quite well. It allows you to work this out easily. Okay, so in the future, we will prove this theorem here. But for the time being, just know that when you differentiate, let's say x to the power of 8 here, d by dx of this, it will be the 8 goes down here. It will be 8x to the power of 7. As simple as that. Okay?